All right, so you got through the first video. Now we're going to start to create the swap chain. We're going to make two more global variables, our VK device and VKQ global variables. We're going to add a dev extents char pointer array. This is a list of the extensions we're going to want to include. Along with that, we're going to add this PRI float variable. This PRI variable tells us the priority for our queue. This tells the hardware which tasks are more important if multiple queues are fighting for the same GPU cycles. 1 is the highest priority and 0 would be the lowest priority. Next, we're going to make our VK device queue create info struct. We can see we supplied the appropriate type for the struct. Then we're going to give it our graphics queue family, which is the index that we found earlier. We're going to say we only want one graphics queue, and we're going to set its priority. Then we're going to make our VK device create info struct. We supplied the appropriate type. We say we only have one queue create info count. We only have one queue. Then we give it our information for a queue. We say we only have one enabled extension, which is our swap chain. And then we give it our list of extensions. Next, we're going to create the device. We're going to give it our physical device, the DCI struct, and then this is going to create the handle to our device. After this, we're going to do our Vulk load device. This is going to give us our device level pointers. We're going to do VK get device queue. This function will give us a handle to our queue, which will be filled in the graphics queue variable. We provide it with the graphics queue index that we got earlier, and we give it the device as well. And just to make sure that everything is going smoothly, like always, we build and run. Seems to be fine. All right, so now I'm going to quickly explain the swap chain. Basically, when you're drawing images to the screen, you're going to have a front buffer and a back buffer. The front buffer is going to be the one that's currently being displayed by your monitor, and then the back buffer is the one that's being drawn onto. And then you'll just keep swapping these out. The back buffer will become the front buffer, and the front buffer will become the back buffer. You can have more than one back buffers, but I've seen only really hear of like double buffering or triple buffering. That's counting the number of back buffers you have. So there's different components of a swap chain, and we'll go through this as we make it as well. But there's the image count, as we somewhat mentioned before with the back and front buffer. The images are what's going to be drawn to the screen or what's going to be drawn to. They'll have the type VK image, and they'll be drawn to the window surface, which is a VK surface K char. We'll check the capabilities with the VK get physical device surface capabilities. It'll tell us things like the window's extent, which is the width and height of the image we're working with, or the surface we're working with, the maximum number of images expected, and the minimum number of images expected for our device surface. Then we'll also check the surface format. You know, this is like our color and whatnot. So, and our bit depth. So in our case, we're going to be using our 32-bit type colors, our RGBA, all being RGB and A, all being, 8 bits. And then we're going to have a color space of nonlinear. And we also have different types of presenting modes. This is determining how the swap actually happens. And just if you wanted to know, here they are. So let's just start setting up the swap chain. The very first thing I'm going to do is above this while loop, I'm just going to do a create swap chain. And as you might guess, this is going to be the function we're going to use to create the swap chain. So I'm going to go up top here, go above main, do a create swap chain like that. Have it be a void function. Why not? We get our capabilities for the device surface. We get the number of device surface formats. We get the physical device surface formats. I'm going to add another global variable, a VK format global variable. Then back in our create swap chain function, we're going to loop through all of the formats that there are, and we're going to see if we can find a format that has that 32-bit color, the 8 bits for red, green, blue, and the alpha channel. Then we're going to make sure we have our nonlinear color space. And if we find that format, we're going to, set our surface format variable to that format. And then we're going to set our swap chain format to that format. And actually, this doesn't really look too clean. So I'm going to do a little cleanup here and do this. Surf swap chain format equals that type format. There we go. And then I can remove this, and I can remove this, and that just looks a little cleaner to me. We'll add a VK extent 2D global variable. And right below the area where we got the capabilities, I'm just going to add this. We don't need that. There we go. So we can just save our global variable for our current extent. And you know what? I was actually wrong about this. I am going to need that that variable up here. So I'm going to switch this again. Sorry for the confusion. And we're going to set format to this like it was before. And then we'll do our swap chain format equals surf fmt dot format like that. Return it to the way it was. Then we're going to create our VK swap chain create info structure. And you can see here in the struct that we're using the VK present mode FIFO KHR. So we're going to wait for the monitor's refresh. So we're going to wait for the VSync to prevent screen tearing. We're going to keep the current transformation. That's like if you wanted to rotate the image 90, whatever, how many degrees. We're going to keep the transformation that it currently has. We're going to use VK sharing mode exclusive. That's because we're using one queue. If we were using multiple queues, we would have to change this, but we're just going to use VK sharing mode exclusive. Then we have clipped as VK true. I believe this does, I think it's an optimization. I think it doesn't display certain pixels. Like it might not display things that are behind the camera and whatnot is my guess. Then we have this variable VK composite alpha opaque bit KHR. That's just telling Vulkan that we're going to ignore the alpha channel. I'm going to make another global swap chain variable. And I didn't do this before, but I'm going to actually include stdlib because we're going to need that in a second here. Go back down. We'll add this if statement and we'll create the swap chain with our supplying it with our info struct, and then we'll fill in the swap chain global variable. So next we do a VK get swap chain images KHR. It's a function that lets you grab the handles to the actual textures that the operating system has set aside for your window. And then we get the count, then we allocate our swap chain images. And then after that, we fill the memory for those swap chain images. Then we create our swap chain image views. We're in the process of creating those. The reason why we create the swap chain image views is because you can't use the VK image handles directly for rendering. So VK image is like the data. It's the actual block of memory that contains pixel values, defines like physical properties, how big it is, what is the format, what MIP levels does it have, and we'll get into some of that stuff a little bit later. Where the VK view, image view, is like the interpreter. It's like a wrapper on the image. It tells the GPU how to interpret the raw bits. It answers questions like the dimensionality. Should I treat this as a 2D image or as a 2D texture or as a 3D single layer or a 3D texture? And the aspect, am I looking at the color part of the image or the depth part? Swizzling, which swizzling is, the red, green, and blue channel or alpha. You can swap the red, green, blue channel if you want. That's swizzling. And then it tells like the range. Am I looking at all the MIP maps or just the one in the top? Next, we loop through our swap chain image count. We create our VK image view create info struct for each loop. We set the appropriate image for that struct. We set VK image view type 2D. We do our swizzling, and here we're just going to keep the red, green, blue, alpha channels the same. Next, we define our sub-resource range members. So I am going to go into map levels a little bit. Don't worry about this too much because it has to do with textures, and we're not going to be adding textures at the moment, but I just want to go through it real quick. So in a nutshell, the MIP level is basically how big of a resolution that texture is going to take up, depending on, and it's dependent on how far away you are from that texture. Why this matters in Vulkan? In your C application, MIP map levels aren't free. You have to plan for them during the image creation phase. And then there's a little calculation that kind of tells you how the MIP map level is determined. And this is just a brief explanation on trilinear and anisotropic filtering. And swap chain doesn't normally use MIP levels because the image is meant to match your window 1-to-1, so it wouldn't really make sense to use MIP levels in the swap chain. Then in our sub-resource range, we're telling it that this image view is for color. This is going to read, we're going to get RGB A values from this. We have one layer. Then we create our image view, or image views, because we're going to make an image view for this whole array. And we'll print off an error if there was an error. All right, and then at the end, we're going to want to make sure to free swap chain image views and swap chain images before we end our program. So let's just build and run and see what happens again. All right, so that concludes the video. In my next video, I'm thinking that I might talk about either command buffers or getting memory from the GPU or both. But I guess you'll just have to wait and see. All right, that's all.